Hello guys, welcome on Tesla Adventures. In this video, we are going to discuss the minimum force required to keep moving a plank with constant velocity on a layer of oil, as well as the velocity profile of the same plank. So in the first case, let us suppose that there is a plank which is placed on a layer of oil, viscous oil, and this plank is moving with a velocity v naught, and to keep this plank moving with the same constant velocity we require a force to be applied on the plank, and we have to find out that force first of all. So we know that obviously this plank, as it will move, it will experience some viscous force in the backward direction, and that viscous force will be cancelled out by the applied force, and then that plank will keep on moving with the constant velocity. Now first of all, we can assume that the velocity gradient of this oil will be constant. So we can assume that the velocity gradient will be equal to v naught by h. Okay, and obviously the viscous force acting will be equal to neta into A, where A is the area of contact of the plank and the oil. So neta A into V naught by H. Okay, and this velocity gradient, area and neta will be constant. So viscous force will be constant in magnitude, and obviously direction will be in the reverse direction. So to keep this plank moving with the constant velocity, so as velocity is constant, as v naught is constant, hence we can say that acceleration will be 0, and 0 acceleration means net force is 0, and net force 0 means that applied force is equal to the viscous force, and viscous force is neta A and v naught by h. Okay, now this is the first case. Now in the second case, let us assume that we have given some velocity v naught to this plank, and as obviously the friction viscous force will act on the plank in the reverse direction, so its velocity will keep on decreasing. Okay, but let us find out the velocity of the plank as a function of time first of all. So in this case, obviously at t is equal to 0, v is equal to v naught, and at t is equal to t, v is equal to v, and v will be less than v naught because velocity will decrease. Now the viscous force will be equal to neta into A, again A is the area, into velocity gradient at that time is v by h, and I'm ignoring that negative sign because I know that I'm just writing down the magnitude of viscous force. So this viscous force will be equal to m into A, where A is acceleration, so acceleration will be dv by dt with a negative sign, and this negative sign shows that v is eventually decreasing with time. So neta A by h divided by m into dt will be equal to dv upon v integration, and there is a negative sign also. The limit of time will be from 0 to t, and limit of velocity will be from v naught to v. So ln v by v naught will be equal to minus neta A by h m, and this is t, and v will be equal to v naught e to the power minus neta A t by mh. This is the velocity, and the graph of this velocity with time will be exponential, so velocity will decrease exponentially, so it would take infinite time to bring this plank to rest permanently. And now let us discuss the heat generation. So we know that obviously the initial kinetic energy is half m v naught square, and the final kinetic energy when this plank will come to rest will be 0. So obviously the heat generated will be equal to change in kinetic energy or loss in kinetic energy. So it would be half m v naught square. So heat generated will be also half m v naught square. But if you need to find out that heat generated calculatively, so you can do one thing, that you can write down the power loss, and power lost will be equal to viscous force into velocity, and viscous force at any moment of time will be this neta a v by h. So it would be neta a v square by h, and power lost can be written as dh by dt, and we can substitute the value of v as v naught into e to the power minus neta a t by mh. So it is e to the power minus neta a t by mh. So what we can do, we can substitute the value of v here, and we can integrate this term with respect to time to find out the heat loss. And the limit would be from 0 to infinity, because at initial moment t is equal to 0, and the final moment when Planck will come to permanent rest will be t is equal to infinity. So the h will be equal to half m v naught square. So this will be the heat lost. Okay, now guys, in the next video we'll be discussing the same thing, but in different scenario, in which we would give some initial angular velocity to a disk which is kept on a liquid on a oil layer, and then we will find out the angular velocity as a function of time. Thank you.